A few years ago, the University of Maine generated a lot of buzz when it unveiled a 3D printed boat.
Go. It's unveiled 3 years ago.
This black cloth is pulled down, and under it is this 25-foot, 5,000-pound black and pretty sleek-looking 3D printed boat, which then gets christened by their senator, Susan Collins. The boat smashes a bunch of records for being the largest solid 3D printed object, the largest 3D printed boat, and it was printed by the world's largest polymer 3D printer in just 3 days. One of the people who's following this story is a guy named Mark Wiesendonger.
And I just thought quickly, if they can print a boat, could they possibly print a house?
Mark's the director of development at a nonprofit housing finance authority called Maine Housing, which, as the name suggests, helps finance affordable housing in Maine. And Maine, at this moment in time, is short on low-income housing by at least 20,000 units. So Mark gets in touch with the guy behind it all, a guy named Dr. Habib Dagher.
Mark had emailed me and said, we have a housing crisis. Can we 3D print the home? And my question was, let me think about this. There's a lot of pros and cons to doing this, and I'll get back to you.
I'm Kathleen Schuster, and this is Living Planet from Deutsche Welle. On today's show, the story of the world's first 3D printed home that's 100% recyclable, the BioHome 3D, how it got made, why it's a big deal for a state like Maine, and how it could be a game changer for the construction sector's carbon footprint. Hi, fine. How are you?
Good, thank you.
The first question's the easiest one. Can you please tell me your name?
My name is Habib Dagher. I'm the executive director of the Advanced Structures and Composite Center at the University of Maine.
I want to go back to the beginning of this idea of a 3D printed biohome. What was the main con that came to your mind when you said, let me think about this?
The big issue was, we knew, of course, there are other people printing homes with concrete. And my concern was that particular technology had limitations, and we wanted to see if we could do something that's more renewable, more recyclable, and more flexible than that. And that's why I went back and did some thinking.
So let's talk about the development of the biohome. This took a few years. At what point did you realize, okay, we have something that could actually work, and we're going to give it a shot?
It was really a convergence of a lot of things that have happened at the same time. One is the fact that we knew that Maine had a major crisis. The second crisis is what to do with the wood residuals or wood waste that Maine has had. We had 7 pulp and paper mills shut down in Maine, and a lot of the wood that used to go to these paper mills, and that's called wood residuals, or if you wish, wood waste from the sawmill process, used to go to the pulp and paper mills, and now it doesn't have a lot of places to go, which is a challenge to some of the sawmills in Maine in terms of what to do with that resource. And we have a lot of it. We have about 1 million tons per year that we generate of this wood waste. So that was one of the issues, is what do we do with that waste? We were also doing 3D printing research, and we've been doing a lot of extrusion research for 20 years. It was really connecting the dots, these 3 dots, if you wish, the resource that exists that has a crisis, the additive manufacturing capabilities that we've developed, and the 20 years of research we've done on these bio-based materials. And that was the aha moment, or the light bulb, if you wish, that says, maybe we can pull all these 3 together and make it work. And we've done quite a bit of research in the lab and testing and evaluation. We printed a boat, and we knew that was feasible. And we knew at that point in time we had a really good shot at making this work.
We're going to come back to why Maine is such a unique setting for this project in a little bit. Before we do that, though, we're going to fast forward through Habib Dagher's story. What ends up happening is several teams, so the one from the University of Maine, local architects, and researchers from the Oak Ridge National Laboratory from down south in Tennessee, begin working together to figure out how to turn what's essentially sawdust into a house. Almost like reverse engineering the traditional way of building a home, but instead of wood, they're only using wood waste. The other key component here is a bioplastic made from corn. And 3 years later, in November 2022, they have their house, the BioHome 3D. And today, you can walk right up and touch it. A few things stand out. For one, it looks nothing like the 3D printed houses made from concrete, which tend to be boxy and gray. It has off-white paneling on the front, and the roof, which is the color of a warm natural wood, has a slight gable that gently slopes and then curves downward on either side to form the two exterior walls that enclose the front porch. Inside, when you run your hand over the wall, you can feel layer after layer of biomaterial that took about 3 weeks to print. Their ridges mimic the natural grain of wood so well that if you step back several feet, the curve of the walls, an effect of printing at a 45-degree angle, looks as if someone took a large piece of solid wood and gently bent it, the way a luthier might shape the curves of a violin. This material might look delicate, but it actually has twice the compression strength of concrete. Another thing about the BioHome is that it's only 600 square feet. Just enough space for a living room, bedroom, kitchen, and bath. But it seems a lot bigger because of how the walls curve up into the ceiling and because it lets in so much natural light.
Not only have we looked at different designs of homes, and we also did surveys of our center staff to say, okay, of these 3 different options, which one would you really want to live in? So we spent a lot of time to try to develop a design that is attractive and people want people to live in.
So then the next winter rolls around, and the BioHome passes its first big test. It survived a full year outside with no major problems, despite braving wind chills of minus 45 degrees Fahrenheit, lots of snow on the roof, windstorms, and heavy rainfall. One thing that has changed, though, is that Maine's housing problem has actually gotten worse in the meantime. Originally, it was short by about 20,000 units, meaning rentals for low-income households. And then the pandemic happens. Suddenly, people from big cities like New York start migrating to cheaper and more rural areas like Maine. Their population of around 1.3 million grows by over 25,000 in the span of a year. Housing prices shoot up by at least 30% in many areas, or in some cases, even more. Here's Mark from Maine Housing, who we heard from at the beginning of the story.
My wife bought her house for $210,000 7 years ago. We were told that it's worth $500,000 to $600,000 today. And I could not afford to buy a $500,000 to $600,000 home.
Now, Mark says, Maine needs roughly 84,000 housing units for all income levels by the end of the decade. And it's not just because of big city folk. Maine's affordability and wide swathes of forested land and scenic coastlines are a big draw for a lot of different groups, like climate migrants from other states and also asylum seekers. Plus, it has the country's oldest population and some of the oldest houses in America, and a lot of them need a major update. So even if you can find a house, it'll cost you. So now the question for the BioHome team becomes, what's the fastest we could scale up production? To begin to answer that question, it helps to get an idea of how the world's largest polymer 3D printer works. Let's start with the numbers. It's 60 feet long, 22 feet wide, and 10 feet high. So picture 2 tracks that run parallel to each other. They're about as long as 4 mid-sized cars. And there's this huge blue frame that moves back and forth along the track as a large nozzle deposits layer after layer after layer of the printing material in the printing bed. In this case, wood flour mixed with a binding agent made from corn that's been heated to its melting point.
So this can be visualized like a glue gun, hot glue gun, where you're depositing and then you're putting like a bead on the top of each other.
Dr. Halil Takenop, who you just heard there, was what they call the co-PI, the co-primary investigator, and heavily involved in developing this material. He's one of the people from the partner team at the U.S. Department of Energy's Oak Ridge National Laboratory down in Tennessee. One of the tricky parts, he says, of 3D printing with polymers, think petroleum-based plastic, think corn-based bioplastic, is figuring out how the polymer will act between the time it's deposited and cools and the time the next layer is put down.
So the polymer molecules are like long entangled molecules that we can think like similar to spaghetti. So in molten form, what happens is they expand. And then because during the extrusion process, we are also kind of stretching them to deposit, and then they're going to start cooling down. During the cooling down process, they actually start to contract because now they're solidifying.
Meaning there needs to be a component that can keep the material stiff enough so that the object that's being printed doesn't, for example, start to curl up off the printing bed. And in this case, it was the wood flour that gave the material that structure. They also printed it at a 45-degree angle, which means they could also build the BioHome in a way you can't with conventional building methods.
You can actually build every part in single piece, the whole module, the roof and other parts, because this is a layer-by-layer process. The previously put layer is your support structure. And if you go very high angle, you don't have enough support underneath. So your material will start to sag and it's going to lose its shape. But if you go 45-degree printing, it actually allows you to be able to print the roof or upper parts without having to have a support structure underneath. That's why it's very unique.
And by being able to print entire pieces of the home, which is why, for example, the walls curve directly into the ceiling, that meant the BioHome was printed in 4 modules. They added insulation and electrical wiring in the lab and then assembled it on site within about half a day. And that's a big deal in Maine, where half of the year it's too cold to build anything with concrete. Not to mention the fact that printing with concrete means you have to print on site, and you're only able to print walls at a 90-degree angle. Another thing that might make the BioHome a realistic contender on the market is that Maine has a lot of sawdust with nowhere to go. So if you're not familiar with Maine, there are a few things to know here. Maine is still about 90% forested and has been one of the leading lumber and paper producers in the states for centuries. Fast forward to present day, and lumber is still going strong, but Maine's few dozen paper mills have dwindled to just a handful. The rest have shut down over competitive prices on the global market, digitalization, and in one case, an actual explosion. Now the sawmills are glutted with, as Habib Dagher said earlier, 1 million tons of wood waste lying around with nowhere to go. And the question is, how many houses does that translate to?
It depends on how big the house is, of course, but let us pick a house like BioHome 3D that we finished. It's a 600 square foot, 1-bedroom home, and that requires about 10 tons of wood waste or wood flour, if you wish, dried wood flour. So if you take a million and divide by 10, that's about 100,000 homes.
He says, of course, they're not going to use all of the 1 million tons of wood waste because there are other uses for it. 100,000 homes is just a theoretical number. In terms of speed, if you added up all of the printing hours, it took about 3 weeks to print the BioHome 3D. Dagher says they were printing at 20 pounds per hour when the project began, and then at 120 pounds per hour by the end of it. And by the fall of 2023, they hit 500 pounds per hour. At that rate, and with 2 printer heads working together, the Composite Center could print the BioHome within about 48 hours. But this opens up much bigger questions about the supply chain, the cost, and ultimately the carbon footprint. The projected commercial cost for the BioHome is about $40,000 since wood flour and bioplastic are relatively cheap, and unlike normal home construction, 3D printing cuts out much of the labor costs, which is ideal amid a labor shortage in the construction sector, which is also making it harder to get affordable homes. That number, though, doesn't account for processing costs, and it doesn't account for the appliances installed afterwards either. It also doesn't tell us what would happen to the costs if this type of production became competitive with wood pellets used for heating, for example. Wood pellets are, incidentally, a growing export in the States. In 2021, the U.S. exported $1 billion worth of them, largely due to a change to EU climate policies.
And the other piece is we need to ask ourselves, is really burning wood pellets, is that the best way to use wood from an environmental perspective? And there are, of course, scientists that have looked at that in great detail. And so we certainly believe that taking that wood waste and locking it in a house, for example, that might be there for hundreds of years and be able to recycle it and use it for new products is a more green way, if you wish, to lock the carbon that our forests extract from the air and keep it locked. So we believe from an environmental perspective, building homes is using this waste material is a better approach than burning the pellets.
They even think it might be possible to recycle the house up to 5 times. There's a graduate student currently researching that, and the team is also still crunching the numbers on the BioHome's carbon footprint. But let's first consider the construction sector's carbon footprint in general, which is huge. According to the United Nations Environment Program, construction accounted for nearly 40% of energy and cross-related CO2 emissions in 2021. That's quite a bit more than, for example, CO2 emissions caused by the transportation sector, which is around 25%. Printing can also cut down on waste streams from things like the materials that have to be thrown away, like, for example, from cutting out the doors and windows.
So if you compare a single-family detached home like BioHome 3D versus a single-family detached stick-built home using traditional construction methods, we're seeing right now about 30% reduction in the carbon footprint when you compare these two options. And of course, that's an initial number, and we may be modifying that as we continue the research. So.
The BioHome still has a few hurdles to clear before it could realistically become a housing solution. Dagger says it's about 80 to 90% there in terms of meeting goals and fire safety standards. But they also need to find out how the materials respond to a few more things, like different climates other than Maine's, or with people living in the house, or how the materials' properties change each time they're recycled. Plus, the design would have to be adapted if they want bigger units, and they're also considering which plants could be used for the bioplastics other than corn. Mark from Maine Housing points out that another challenge will be moving production to the private sector and keeping it cost-effective. The material itself is easy to ship. After all, it's in the shape of wood pellets, and pellets are already being shipped on a mass scale for heating. But to make this work, private companies will have to have the right 3D printing technology.
We can see the path, and just looking at numbers that we have available right now, we know it's possible, but it still remains to be seen how it's going to work exactly.
BioHome 2.0 is coming soon, and a nonprofit that fights poverty called Penquis is going to help choose someone to live there. And then they want to print 8 more homes to be used first and foremost by homeless people. Technology aside, Mark thinks another important feature of this house is that it's incredibly livable. In fact, that was one of their goals when Maine Housing worked with the architects on this project.
At the end of the day, the less it costs per unit for us to create housing, the more housing we can create. It's the number one factor in how we do our work. That said, we don't want to create a home, these are people's homes, mind you, that are not comfortable, durable, and attractive. A home with natural light and pleasing finishes, something that's pleasing to the eye, is going to make for happier people. With this particular project, we were part of the design process, and we specifically wanted to make sure that it met our design standards. We did work with a local architect to help create it, but we wanted to make sure that it was livable and also accessible for people with disabilities. And they nailed it.
I wanted to close this, though, by asking you, what's your favorite feature of the house?
Well, just quite frankly, aesthetically, if you go into the bedroom, because it's printed at a 45-degree angle, the way the layers of printing look as they go around the rounded ceiling, it's actually aesthetically very pleasing. It is very cool looking. I love the fact that it's completely recyclable and it doesn't have huge impact on the environment, and it's going to be super insulated and cheap and all that stuff. But at the end of the day, it looks cool.
We'll be right back after this message from DW.
This is the story of the biggest cannabis scam ever.
This is the story of juicy fields.
I've lost 20K.
I had 350,000 euros in the account.
And the scam might just continue.
We have owners that sometimes like to be flashy, hence why they like cannabis and crypto.
This is Cannabis Cowboys.
A story about big dreams,
juicy money,
and never-ending hype.
Today's episode of Living Planet was produced by me, Kathleen Schuster, and edited by Neil King. Our sound engineer was Gad Georgi. Mark Wiesendonger spoke to us from Augusta, Maine, and Dr. Habib Dagher was in a sound booth in Orono, Maine. Dr. Halil Teganab spoke to us from the Department of Energy's Oak Ridge National Laboratory in Oak Ridge, Tennessee. A quick note about the partnership between those two institutions, which we didn't go into in our story. The University of Maine and Oak Ridge National Laboratory are part of a wider research network known by the acronym of SMART, which is sponsored by the U.S. Department of Energy. The BioHome 3D is one of SMART's moonshot projects. Special thanks to reporters Nicole Ogrisco from Maine Public in Portland and Caitlin Boudion in Bangor for assisting DW with on-site recordings, including in the BioHome. To download this and past episodes of Living Planet, go to Apple Podcasts, Spotify, or wherever you get your podcasts. You can also find us on YouTube by going to DW Podcasts. Don't forget to hit the subscribe button. We're also available on DW's website, www.dw.com. Thanks for listening. Living Planet is produced by DW in Bonn, Germany.